any dam system. Okay, the only thing is you should, whatever the circuit is or whatever the architecture is there from you, you should draw a proper DFG. Once you have a DFG, then through a retiming you can improve the performance. So yesterday when we talk about the retiming, at that time we talk about this equation. Okay, when we talk about the retiming through retiming vector. So at that time we have observed that if a weight of U to V node, where U is a source and V is a destination, and data is flowing from U to V. So at that time, if I apply the retiming concept, then for that particular edge which going from U to V, for that the retime value of the weight after applying the retiming value, after applying the retiming concept, is a old value plus RV minus RU, and the retiming solution is feasible when this weight is ultimately zero. Weight is nothing but the that delay element that we are talking about related to the your related to your age. Okay, now for that weight has to be 0 or positive, because that defines the number of delay element, and that has to be either it is an absent, we are defined as a 0 delay element, or maybe 1 2 3 4 like that. Okay, then probably this is a some standard one. This property that in a particular loop total number of delay element is same before and after applying the retiming. So for that we have seen one small proof also, that how you can actually prove that the number of delay element is before and after the retiming same. Okay, so ultimately in a retiming we cannot bring the any delay element outside the loop, but we need to manage or we need to rearrange the position of a delay element whatever available inside the loop for the purpose of breaking the critical path. Okay, because ultimately the whole game is to reduce my critical path. So in order to reduce the critical path, I will change the position of my delay element. Now these two method, retiming with the vector, that we have yesterday seen, retiming with the cut set, that we will see today. Just to refresh that what we have done, that for a retiming with the vector, if you remember, we talk about this particular graph U to V, where the weight is W is equal to D. Okay, now for that, and there is a, okay, so there is a, if this particular graph, when I have a U to V, and if I define a new retime graph, then for that W new would be like this: W plus RV minus RU. RV and RU you need to choose anything. Here RV and RU is being chosen as a 1 and 2. Okay, so it is up to you, but ultimately you need to ensure that W new has to be greater or equal to 0, and RV and RU you need to choose accordingly. So this way it will work. Okay, so even this example where we have replaced with 2D and then we have seen it. Now when we try to solve this with the retiming vector method, what happens that we used to assume some value for a retiming vector value, that RV and RV we used to assume. Now when you have a DFG where you have a large number of nodes, okay, so at that time it would be difficult. Okay, sometimes you observe that whatever the retime value you have choose initially for that node, it could not be valid, because what we have seen that once we fix the retime value of a particular node, then we need to also see its implication of the different other edges. Okay, so at that time also we need to ensure that whatever the weight that you are getting, there has to be greater or equal to 0. Okay, so sometimes when you have so many nodes, so at that time it would be difficult to actually identify a RV and RU value in one shot. At that time you need to go for trial and error. That is some hit and trial, that you will choose some RV and RU, because yesterday only we have seen that RV and RU we have taken 1 and 0. You can took 1, 2 and 1. So ultimately that difference has to be 1. Okay. So that you can take anything. Now, but when you have a larger number of nodes, so at that time it may happen that what you have started with, and when you apply it for a different edges, then you will observe that you are not able to get that condition which is mandatory to satisfy. That is, your weight has to be greater or equal to 0. So at that time what happens that you need to keep on changing your RV and RU. And as the number of node goes increasing, your RV and RU value that you need to choose, that should be some sort of tedious job for you. So now, in order to do the retiming, what you can do, that there is another method which is far better or more efficient than a retiming vector method. Okay, that is a cut set retiming. Now, cut set retiming is a concept which is similar to known to you. Okay, but let me explain it. So I am just going to the blackboard. So what we are interested in, the retiming with cut set. So that is the second method we are interested to discuss. So let's take a same example what we did yesterday. You have a U, you have a V. There is a one edge where D is being defined here. There is another edge where D is not being present. Okay. Now I want to first understand the concept of cut set. So what the concept of the cut set says that, let's say that I have some node like this, where there is some sort of loop. Okay, so there are some nodes and there are some loops in my graph, that is a DFG. Okay, now what the cut set concept says that, okay, and there may be some internal connection also like this. Okay, now what the cut set concept says that I need to cut some edges. Okay, and I need to cut the edges such a way that when I cut the edges, then I will get two different graphs. So here maybe if I cut these all edges, so whatever the edges which is being cut, that I need to remove. Okay, so whatever the edges which are being cut from the cut set, that has to be removed. So I will remove all these edges. Then if I observe that, then you will find out two graphs. One is a G1, another is a G2. So that I define as a cut set. So ultimately, I need to cut my edges in a graph such a way that I will get two different graphs, or maybe some set of graph, or maybe two different representations, which I can consider as a G1 and G2. So that is a cut set. So only thing is, whatever the edges which is being cut through that particular cut set, you need to remove them. And after that, whatever the remaining, that you need to see as a two set. One is a G1, another is a G2. Now, in a cut set, when I consider a cut set with a retiming, so of course the first step is you need to apply a cut set. Now second concept which says that you need to, now retiming concept is already we have seen that we are interested to insert a buffer. Where we want to insert a buffer? We want to insert a buffer at a critical path. So critical path is a delay-free path where there is no delay element, or in a simple say, the D is I am considering as a buffer. Okay. So in a critical path, I need to insert a delay element. So that means ultimately in a retiming, I am interested in inserting a delay element. But then whatever the one property says that the number of delay element inside the loop should remain same. So that means if I insert a delay element, then I need to remove that somewhere from a loop. I hope you are following me. Because inside a loop, if the number of delay element remains same, then when I say that I am inserting a delay element, then in order to do that, I need to remove the equal amount of the delay element from the same loop. Okay. So now in a cut set retiming, what happens that when I apply the cut set, then you can actually apply, let's say that for all these edges, I am providing or I am inserting number of delay element. This k is any integer number. So k could be anything. 1, 2, 3, 4. So for a number of edges, I am applying or I am inserting some delay element. But now, as the number of delay element inside the loop remains same, I need to remove the same number of delay element from a loop. So what this concept says that if I am applying plus kd, then somewhere over here I need to remove minus kd. So for this particular loop structure, overall, if you observe that the number of delay element is preserved. Because in a loop, I can't change the number of delay element. But of course, I can insert a delay element by considering the case by I need to remove it from somewhere. So that means if I insert k number of delay element, then in those loop, I need to try to remove the same number of delay element. So overall, the picture is the number of delay element inside the loop is same. So that means if I apply plus kd, then I need to do it minus kd. Okay. Now in a cut set retiming, if we want to do that, then what we can do that? Let's say that here the edges are going from, I am defining this is a G1 and I am defining it at a G2. So when I say that edges which at the top, all these edges from G1 to G2, they are going. Over there, I am applying plus kd. So I need to remove minus kd where the edges are going from G2 to G1. That means if from my left hand side, the edges which are going on the right hand side, where I am inserting the delay element, then equal amount of the delay element I need to remove for the edges which goes from the right hand side to left hand side. So that means from G2 to G1, whatever the edges they are going, I need to remove the total number of delay element. Why I am doing so? Because the total number of delay element inside the loop should remain same. Okay. So this is very easy. Okay. So what it says that in order to apply the cut set retiming, the first thing is you need to select the cut set. You need to select the cut set. Once the cut set is being selected, then you need to apply the case where you are putting plus kd when the data is moving from G1 to G2, then you are inserting the plus kd, that means you are inserting the delay element, then for the reverse edges you need to remove the delay element. So just the concept says that, so with that the total number of delay element inside the loop remains same. Okay. Now this could be reverse way also. Okay. It may be कि G2 to G1 में मैंने plus KD किया, then G1 से G2 में minus KD apply करूँ. So both are possible. Okay. For either of direction, if I am inserting the delay element, then for the reverse direction, I need to remove the equal number of delay element, so that my loop has a same number of delay element. Is it clear? Okay. Now try to understand this with this particular example. So here, if I look at this particular example, Then there is edge U2V, which I am defined, let's say that E1. So there is E1 which goes from U2V, and there is E2 which I am defining this is V2U. Now here the number of delay element is 1, and here the number of delay element is 0. Okay, so when I think about applying a retiming concept, then first of all I need to observe the critical part. Now yesterday we have seen that if I consider this as a T, this as a T, then this would be the critical part, because this V will take a time a T, this U will take a time T and twice T, and that there is a zero delay element. This has to be performed in a 1 clock cycle. So with this I can define my frequency would be 1 by 2T. So minimum period or critical part delay is twice T and the frequency is my 1 by 2T. So ultimately this edge, which is a delay free, I need to insert a delay. So I will apply the cut set retiming concept over here. So which edge you need to cut? Okay, so cut set you can apply at, if in a graph you have, let's say that 100 number of edges. So out of 100 number of edges, for which edges you need to apply the cut set? So edges which includes in a critical part, because our intention is clear, because our focus is for a critical part. For a critical part where it is a zero delay free part or a zero delay part, over there I need to insert a buffer. In order to apply this particular concept, I will apply the cut set for those edges only. So now what I will do, I will just consider this edge. Now if I want to apply the cut set at this edge, then ultimately I need to apply the cut set like this. So now U and V, you can consider there is a two different node which I consider as a G1 and G2. Now by applying a cut set, my mindset was I need to insert a buffer. So that means I am interested to insert a buffer over here. So that means the edge which goes from V to U. V to U, that means let's say that this is G2 graph, this is G1 graph. From G2 to G1, I need to apply a plus D. I need to insert a buffer, because this is a critical part. In a critical part where I found that it is a delay free part, I would like to insert a delay. By inserting a delay, okay, so that was T plus T. Now it has break. So now it is no more delay free part. But as per this particular discussion, what we just saw now from this particular graph, if I apply from V to U plus D, then from U to V, I need to apply minus D. Because in a loop, ultimately the number of delay elements should remain same. So if from V to U, where I am talking about G2 to G1, where the edge is going, I am inserting a plus D. That means I am applying plus D concept. But now U to V, I need to apply the minus KD concept. Here I have taken K is equal to 1. So that means if I have done a plus D, then I need to do a minus D over here. So with this, if I consider the retime graph, then retime graph would be like this. U, V, here it is D, but here it has removed. Now it is TT. Now if you remember, yesterday through a retiming vector also we got the same solution. In order to break the critical part, we are putting D over here, but then it gets removed from my top edges. Okay. Now then we have seen the another example where I am putting this 2D. So let's Okay, so just slightly I am changing this graph where I am putting this as a 2D. Okay, and here again I have a, this is my E1, this is my E2. Now V2U, sorry, U2V, here I have a 2 delay element. Okay, from V to U still I have a 0 delay element. But still the critical part is V to U, where there is a 0 delay element. It is twice T, F is equal to 1T, which I want to reduce it. So now again I will apply the cut set. Still the critical part is same. So that means whatever the cut set that I want to apply, that is remain same. Okay, so that remains same. Now, as this is a critical part where my intention is to insert a buffer, so I will apply plus D over here. So that means for V to U edges, I have applied for this particular edges G2 to G1 where I apply plus D. So that means for U to V, I need to do minus D. So that means, so now what happens that this D is there, but this 2D minus D. So that makes D over here. So now this graph, for this particular graph, the critical part delay is changed. Now for this particular retime graph, if I talk about this particular graph, my minimum period is T, and with that the frequency is 1 by T. So that means my frequency is improved and my critical part delay, this I am defining as CPD, that is being decreased. So now this would be the solution. Now if you remember it, yesterday through retime vector we solved this example and we got this output. Okay, so this solution is very efficient, where just you need to observe a critical part. For the critical part, you need to apply the cut set, and then you need to apply the logic of plus D minus D. That means plus KD minus KD accordingly. Okay. So let's try to understand it with the example. Okay, let's consider the few examples. So I am just going back to my PPT. Yes, students, any doubt? As I said that if you have doubt, then just speak that. Otherwise, it would be difficult for me to actually see the chat box every time. Okay. Now,
Sir,
yes.
sir, in the second case, we have changed U to V delay element to 2D.
In the second example, that is the phrase example. Yes, we have changed it to that D to 2D. Yes.
So in the first case, we cannot apply retiming, right?
In a first case, actually, we have applied the retiming, but by applying the retiming, we are not getting the improvement in performance. Still, the cut set we have applied a plus D minus D concept, but with that, what happens that the performance of the graph or performance of that particular circuit is not improved. The only thing is the critical part has changed now because of the deletion of the edge from U to V. Previously U to V there was a D, and V to U there is a no D. But by applying a cut set retiming, we are able to provide V to U, that is a delay free part, a D, but U to V gets cancelled. So that is because in a loop, ultimately the number of delay element has to be same. So for U to V node, as we observed that there are two edges. So either of one edges is having a D, then by applying the retiming only, what you can do that you can shift your critical path, but still the performance of the circuit is same. So the answer for your question is we did apply the retiming concept, but the performance of that DFG is not improved because of the limitation of the number of delay element inside the loop. But in a second example where we observed that particular edge U2V now having a 2D. So as we have a 2D, so there is a flexibility that if I insert a one delay element, then that makes a one delay element lesser in U2V edges, but still as a presence of the delay element, the critical part is still broken, and because of that now the minimum period is reduced to T, and that is the optimized one. I hope you got the concept.
Sir,
Yes.
sir, can you explain the retiming by taking three notes?
That's what I will give you the example, but not three, with the four nodes.
Okay,
Just
sir.
now in the PPT. Okay.
Okay.
So this is an example. Okay. So I am explaining the example with the cut set retiming. However, one can solve with the retiming vector also. But if it is not being asked, then cut set retiming is a efficient method. Okay. Now this is the four node A, B, C, D. Okay. All nodes are being connected through some edges. Now whatever the value which is being returned, just observe 10, 20. This A is having a 20. So that defines the execution time the node A will take to complete the task. So as I said that in a previous class, A, B, C, D, whatever the nodes are there, those nodes are nothing but a functional unit. But when I reflect them in a DFG, then they are a simple node. They can be multiplier, they can be adder, even they can be your Cordic block. But as it is a one functional unit, it will take some time. So that time is being defined. So A is having a delay of 20 units, B is having a delay of 10, C is having a delay of 10, and D is having a delay of 5. And all these particular nodes are being connected through some edges. Okay. Now, for this particular example, how many loop you have? Okay, how many loop you have?
Two.
Two loops, sir.
Two
Two loops are. Okay. So now all of you just calculate for each loop how many delay element you have. So consider this A, B, C, A is a one loop. B, C, D, B is a second loop. So A, B, C, A, how many delay element? 2. B, C, D, B, how many delay element? 1. Why I am calculating in prior? Because I need to ensure that if I apply retiming, then the total number of delay element after applying the retiming should be same. Okay. If it is not same, then the functionality which is being provided by DFG gets changed. So A, B, C, A, 2 delay element, B, C, D, B, 1 delay element. So this is a position where I am starting my concept, retiming concept. Okay. So now retiming concept when I want to apply, then first what is the first thing that I need to look for? I need to look for a critical path for this particular graph. Now what is the critical path? Critical path is a delay free path where I get the maximum execution time or maximum delay. So what is the critical path over here and what is the critical path delay? Critical path is a path, and when I say critical path delay, then that is a value. CDB. If you consider CDB, then it is 25. 10 plus 5 plus 10, 25. And A to B is 30. So that means the critical part is A to B 30 because A to B having a more value. Okay. So A to B is my critical part. Is it clear? So as A to B is my critical part, then I need to look for applying the cut set for A to B. We have just talked about that. If we need to apply the cut set where my critical part lies. So that means I need to apply the cut set at A to B. But for A, there is another edge also, which is coming from C to D. So when I apply the cut set, then it will cut A to B as well as C to D. So that is the second graph. Just try to observe over here. Okay. Try to observe this particular graph. In this particular graph, you just observe that there is a cut set which will cut the edge from A to B as well as C to D. Now when I cut it, at that time intention was clear. What was my intention? Inserting a buffer. Where I want to insert a buffer? A to B. So that means I will apply plus D where the edge is going from A to B. So from A, if I consider for node A, whatever the outgoing edge is, for that I am applying plus D. So that means for the incoming edges for A, I need to apply minus D. I hope you are with me. For A, if I look at the node A, because here for G1, if I consider G1, then G1 is having a node A only. While G2, you can have a B, C, D. So now concentrate on G1. So for a G1, which is node A, for G1, the outgoing edges is A to B, where I am applying a plus D. For G1, the incoming edge is C to D. So where I need to apply forcefully minus D. Because I need to ensure that the equal amount of the deletion I need to go through for my cut set retiming. So as I am applying the plus D, I need to apply the minus D. So with this, the new solution, so this is just cut set, and with this, the new solution will be like this, which is this graph, where you observe A to B, there is a delay element, and from C to D, there is a absence of delay element. Previously, it was present. Just observe. In original graph, it was present. But now, as I apply over here A to B, a delay element, then this prompts that this D will remove the D from C to B. I hope you are with me. Okay. Now, I have applied a retiming concept. What is the critical part?
C to A.
C to A. What is the
C to A.
critical part delay?
30.
30.
So that means before applying the retiming concept, I was at the same position, because for me the delay is important, because I want to increase the frequency. Previously also the frequency is 1/30 unit. Now also the frequency is 1/30 unit. So that means still I am not satisfied. I am not satisfied because still the critical part delay is same. So now I will think about, so C to A is a critical part. So that means for this particular edge, I need to apply the cut set. So that means I need to apply the cut set like this, where it will also affect the B to C line and C to D line along with C to A. My intention is for C to A, but as I need to also take care for this node C, all the edges. So that means I need to apply the cut set like this. Okay. So with this, you will observe that there are two different graphs. Okay. Now, if you observe it, that what was the critical path? C2A. So where I need to insert a buffer? C2A. So for C2A, just for node C, it is outgoing edges. For node C, it is outgoing edges. So that means for C, which are outgoing edges, for that I need to apply plus B. So in a reverse way, whatever the incoming edge is, for that I need to apply minus D. So that means from C2 I expected there is an insertion of D. C2D also there is an insertion of D, and B2C the D would be, so D minus D is 0. So your solution will be like this final, this one. See, number of delay element is not important. The total number of delay element inside the loop is important. Now, what was the initial delay element? I asked you to write it down. What are two loops you have? Yes, MTech. You are also, I asked initially that. Write down the total number of delay. First of all, I asked you to identify two loops. What was two loop?
A, B, C, and B, C, D.
A, B, C, A, B, C, D, B. How many number of delay element you have? A, B, C, A? 2.
2.
After applying the retiming, how many you have?
2.
2.
B, C, D, B. Initially, how many delay element you have?
1.
2. 1.
It was 1. Now, how many delay element you have?
1.
1.
One.
So, in a loop, the total number of delay element same. See, for me, the number of delay element is not a matter. As far as in a loop, why it happened? For that also I am saying. B to C was a common edge. See, previously B to C, when there is a edge, then there was a common edge. So when I am considering A, B, C, A, this B is counted, and when I consider B, C, D, B, at that time also it was counted. But when you actually think about the two loop, then this B to C edge was a common where I have a delay element. But now this common edge has got nothing to do with the delay element. So with this, I need to transfer this common edge delay element to this particular loop to C2A and C2B. Okay, so that's why the number of delay element gets larger when you see this particular graph. But when you just apply the concept कि previously B2C common edge थी, तो common edge थी जिसकी वजह से वो delay element मैं 2 बार काउंट कर रहा था दोनों लूप के लिए, पर अभी वो कोई भी कॉमन एज नहीं है. आपका ए बी सी ए और बी सी डी बी कोई भी कॉमन एज नहीं है, जिसकी वजह से आपको ऐसा लग रहा है कि टोटल नंबर ऑफ डिले एलिमेंट बढ़ गए, पर एक्चुअली अगर आप दो लूप को सेपरेटली देखो तो नंबर ऑफ डिले एलिमेंट आर सेम. आई होप एमटेक यू आर आल्सो गेटिंग द कॉन्सेप्ट.
सर तो लूप में सेम होने चाहिए डिले एलिमेंट्स.
वो तो हमने लास्ट वीक सॉरी यस्टरडे प्रूफ के साथ देखा है. इफ यू रिमेंबर दैट वी हैव अप्लाइड अ रिटाइमिंग वेक्टर फॉर्मूला एंड थ्रू व्हिच we have just write down a theorem that in a loop the number of delay element before and after retiming should remain same.
Yes.
And fundamental for that is if it is not same then your functionality would change. Yes, any doubt? Okay, so good question. So the question that BTech girl has asked that where I need to stop. Okay, now for this particular graph, initially the delay was 30. Now the delay is
20.
20.
Now what the best I can get for this? is the delay for a one particular node which is maximum. See, A is taking 20. Now anyhow, the A which represent one particular functionality, that is taking 20 unit time. Now I cannot change the functionality because I want a same functionality from my graph. So I cannot change A. As I can't change A, then there is no way that I can now get it below 20 because this 20 is assigned to this particular node A. So in this particular graph, the what base I can get is 20. So in short, in a particular DFG, you need to look at a node which is taking a maximum
Excuse
time.
me, sir.
So that is the 1 minute. Let me finish. Okay, then I will come back to you. So in a graph, you need to look at the node which is taking a maximum number of time. Then there is a possibility that you can get a best retime graph where you can have a critical path delay as good as the execution time of that particular node. Beyond that, you can't go. But that is a possibility. It is not guaranteed that always you can do that. So for this particular graph, I can say that 20. Now beyond 20, I can't go. And there is no meaning of shuffling D. If you try to apply also, then you may consider that you may end up with your first one where you have started. Okay. So now for this particular graph, you can't go beyond this. So now I will stop over here. Now consider that this is the best performance that I can get. Okay. Now I think one of the MTech students is asking something. Please go ahead.
Sir, it is not regarding question, sir. Actually, sir, please use some highlighter so that we are not getting confused at which point you are right now.
Okay. Actually, that I will take care of that because actually the problem is that this is a PDF. So in a PDF, it would be very difficult to actually write down anything. I'm not sure. Is there any, or I need to find it out. Maybe if it is a means PowerPoint, then probably there is a pointer I can use. But I will find out next time. Okay. So that it can be done. Or if you want, then I can explain the same example through whiteboard. I am more comfortable with this. Okay. So maybe the next example that we want to discuss, that I will use it with the board. Okay. So let's move to the second example. My FIR filter, 3-tap FIR filter. This is the equation. Okay. So let me go back over here. Let me okay. So 3-tap FIR filter. So when I say 3-tap FIR filter, then equation is fixed. Yn equal to A into Xn plus B into Xn minus 1 plus C into Xn minus 2. This is a 3-tap FIR filter. Now, I want to understand the retiming concept with this 3-tap FIR filter. Okay, which is one you can consider the simplest DSP circuit that you have. So when I understand this, then ultimately I have a Xn. That Xn is being multiplied with the multiplier where I apply A. Then it will generate A into Xn. Okay. Then whatever this Xn is there, this Xn, if I apply a 1D, see for this Xn, if I apply a D, then what will be the output? It is Xn minus 1.
Xn minus 1.
Okay. So for this Xn, if I apply D, then ultimately here I am getting x n minus 1. So that I multiply with b, then that will generate b into, this is my output. Okay, so this is b into x n minus 1. Now whatever this x n minus 1, if I apply again a d, then I would get at this particular point x of n minus 2. That I will multiply with c. Then I will get c into x n minus 2. So I have generated this term, and this term. Now what I need to do? I need to simply add it. So I will just add this. Here I will generate axn plus bxn1, and if I add with this, then I will generate my yn. This is just, you can consider a one sort of representation, which I can say as a graphical representation of my 3-tap FIR filter. Okay, so what you need to understand is, whenever some mathematical expression is given, for that expression also you should able to define one particular graphical representation. Still, this is not DFG. Okay, because in a DFG we have a node only. We want node and their delay. We doesn't want to know that what this node is doing. If you have just remember till this point, we are talking node U, V. In a previous example also we are talking about A, B, C, D. Now this A is performing what functionality? For me, I am not bothered about it. What I worry about it, what is the time which is taken by node A? What is the time which is taken by node B? Okay. So here ultimately for this I should know what is the delay. So what I believe that for a multiplier it has taken 2. This is just a wild guess. Okay. So when you are implementing and you have designed one particular adder, you have designed one multiplier, then you know the delay. What is your delay? Okay. Just to explain you, I am taking multiplier as a 2-unit delay, adder is a 1-unit delay, and my assumption is also reasonably good enough, because always your multiplier would take a larger time than your adder. It could be 1.5 times or maybe more than that, but just to deal with the integer only, I have taken it 2. But of course, if adder is taking 1, then multiplier will take more than 1. That is sure. It could be 1.5 times than adder or maybe more than that. So I have taken this as a 2. Okay. So ultimately now I consider that this is particular node. I will define that this node with some number, let's say I am defining this as a x, this is y, this is z, this is a, this is b. For a DFG, this naming is good enough, and along with this, so whenever I use a, whenever I use b, which actually represent the adder, and delay associated with them is 1. When I use x, y, z, probabilities a is also integer, so maybe just to avoid the confusion, let's put it another. Let's consider this is n and this is n, just to avoid the confusion, because a, b and c is your coefficient value, and here I am talking about m and n. I am just labeling the node. This m and n are labeling of my adder, and this x, y, z are labeling of my multiplier. I can apply any label. Okay, just to replace this in a DFG graph, because for a DFG it is simply x, y, z node. For you, you know that x is multiplier, y is multiplier, z is multiplier, but that understanding is not required when you go for a DFG based optimization. ठीक है. So just I want to now apply a retiming concept. So for a retiming concept, I need to understand the critical part. What is the critical part? Yes, MTech.
X of n to C x from starting from x of n after passing two delays, that will be the critical one.
No. When I say critical part, then for a critical part there won't be any delay. So probably this could be. So see, D is over here at this particular rate, but I am talking about the xn to my x. Then I am talking about m. I am talking about n. This is a critical part where I have a 4-unit delay. If I look at another way, then this is could be also critical part where I consider only y, m, n. Still it is 4 unit. Is there any another part where I have a 4 unit or more than 4 unit delay? If I consider this, previously I thought this, but it is 2 plus 1 only. Okay, I think you are asking something.
So Xn should also be considered as a node.
Xn is my input, yes. Xn is my input. So for that, input is always considered as a one node. But for input, I am not taking about the delay. For Xn, I am not considering any delay. I am considering that input is coming directly. Okay. And for the edges also, for a DFG, for the edges, I am considering only a wait. Wait, that means the connection with the buffer. But edges delay is also we are actually not considering. So for this, if I consider a critical path, then it will be this xn, mn, where there is a 4 unit, or maybe I can consider y, mn, which is of 4 units. Okay. Actually, this problem is slightly simple. Okay. Why it is simple? How many loop you have?
Zero.
There is no loop. So if there is a zero loop, then one property for a retiming, we need to just ignore now. The number of delay element inside the loop remains same. And because of that, what we need to use it, we used to do it, we apply or where we insert a number of delay element, then equal amount of delay element we need to remove. So cut set is also a concept where there is a loop, and at that time we need to put it plus kd minus kd concept. Okay, this in this example there is no loop. So if there is a no loop for your retiming concept, then that allows me to insert a buffer without worrying of removing it. Because if there is a loop, then I need to always ensure that if I am inserting at some place, then I need to remove it. Why I was removing at the time of inserting? Because number of delay elements should remain same. But as there is no loop over here, I do not have to worry about it of removing it. I need to just think about inserting it. Okay, but still when I am inserting, I need to ensure that the functionality should remain same. Okay. So now I need to still break the critical part. So for that, maybe these two critical part is there, So I may think about taking a cut set like this. Maybe. Now I have a flexibility that I can simply insert a buffer. So I will insert a buffer D and D over here. Should I need to insert a D over here to take this cut set? Yes? You can. Alright. Okay, I think there is a 11-2. So that's why Nanda sir is also calling me. Okay, just think about it. See, one thing is sure that we do not want to change the functionality. So by inserting a D, what happens that this adder now getting a input of a one sample delay. Okay. And this is the another adder. Now, if I do not provide D over here, then one thing is simple that whatever the adder, the previous functionality is being achieved. It is not the same now. क्योंकि एडर में पहले जो सैंपल आ रहा है अभी वो एक डिले के बाद आ रहा है तो दूसरे इनपुट का सैंपल भी उसी डिले के बाद आना चाहिए. Are you getting? It is something like that. If we want to start our VLSI SPA lecture, if I come 15 minutes late, then for you there is no worry that nothing will gone for you. You can also come 15 minutes late because the lecture is not started. If both are coming 15 minutes late, then it's okay. There is no worry about it. Okay. But if I came early and you are not coming, and if you came and I am not coming, then there is an issue. Okay. So over here, if this guy is a late of a 1 clock delay, where it provides the input to adder, then this guy is also late. It has to be late. Otherwise, if we count the previous value, then functionality gets changed. अभी सेम कॉन्सेप्ट आपको यहां पे अप्लाई करना है कि ये एक्शन यहां पे ऐसे कितने डिले के बाद आता है. यहां पे डिले अप्लाई करने की जरूरत है या नहीं. जस्ट ट्राई टू ऑब्जर्व. दूसरा एडर है लेकिन फंक्शनैलिटी तो वो जनरेट कर रहा है वाईएन के लिए. सो दैट इज just maybe you can take some array and for that you can consider 3-4 element and try to observe that what is the output you are getting and whether by providing only 2D you are getting or not. This will actually help you to realize the concept of the your retiming. Okay. Okay, MTech, I think there is a small exercise for you. You just realize it. Actually, when this kind of case, when there is a no loop, you have a liberty to insert a buffer, but still that thing you need to take care that functionality should not be hampered. In a loop, when you apply plus KT minus KT concept, then with that automatically it has been proven that if the number of delay element remains same, then functionality doesn't change. But over here, there is no loop. Then you need to think about that how a particular block is getting an input. If one block is delayed for a 1 clock cycle, then it should be applicable for now all. Otherwise, it gets changed. क्योंकि यहाँ पे पहले xn minus xn आ रहा है. अगर वो xn minus 1 है, तो वहां पे xn minus 2, xn minus 2 में भी इक्विवेलेंट डिले आना चाहिए. I hope you are getting my concept. Okay. Try to visualize this and next time when we will meet, we will discuss. Okay. Okay. Any doubt, MTech?
No, sir.
Okay. So when we will meet next time, then we will see this. So I have not anyhow provided you the PPT, so you don't know the solution also. So just try to go through it.
Okay, sir.
Okay. Okay. Have a nice day. Maybe I can take or a. इसलिए मुझे है ना 2 घंटे का क्लास पसंद है क्योंकि ये आधा अधूरा कॉन्सेप्ट रह जाता है. हेलो. हाँ सर, मीन्स बच्चे तो बैठे हैं अभी, मुझे पता नहीं नंदा सर का कोई सब्जेक्ट आप ले लिया है, सब लोग हैं. हाँ ठीक है सर, आपके स्टूडेंट्स हैं यहाँ पे. ठीक, ओके, हाँ चलो. ओके. फॉर अटेंडेंस एक पेपर पे अटेंडेंस ले लोगे? अदरवाइज आई नीड टू स्टार्ट माय लैपटॉप बिकॉज मुझे यहाँ पे अभी एक्सेल शीट डाउनलोड करनी पड़ेगी वरना. ठीक है. आई बिलीव दैट 3, 3, 6 and 12, total 12 students are there. Okay, maybe you can give me. हाँ कमलेश जी बोलो. नहीं मैंने आपको सारे पेपर नहीं आपको मैं फोन कर रहा हूँ वो करेगा. आप टेक्निक प्रोसेस चालू
I was planning to take a